Okay, last time we defined the rate of change of momentum in this equation to be equals to the force. So this is Newton's second law, and there's a direct consequence of this, which is called the theory of conservation of linear momentum. So we know that, let's start. So we have that dp by dt is defined equals to f. So naturally, if f is equals to 0, then this implies that dp by dt is equals to 0, and this implies that m times v is equals to a constant, right? So what this basically means is that if the force is equal to 0, if there is no external force on any particle, then its momentum is going to be conserved. And conservation basically means that the momentum is constant, right? That's what it means. So this is called the conservation for the linear momentum of a particle. And yeah, so the next concept we want to talk about is the concept of angular momentum. So angular momentum is defined to be the cross product of the position vector with the momentum. So the order is very important here because the cross product is not commutative, right? So this is not the same thing as P cross R. Notice this is not an X, this is a cross. It's a bit difficult to, maybe if I make it small, it's more apparent. So the cross product is not commutative, so R cross P is not the same as P cross R. So now, how do you take the cross product? I'm going to show that to you. The cross product is basically the following. So R cross P is equals to the unit vectors x, y, z, rx, ry, rz, px, py, pz. This is the determinant. And this is just x times this minus this times this. So this is ry times pz minus rz times py plus y, and then that's this times this minus this times this. So rz px minus rx pz, and then the final component is just rx times py minus ry px, right? So this is how you take the cross product of r and p if we are working in Cartesian coordinates, right? So now there's similar concept for the angular momentum as with the linear momentum. So what we do is we define the external the external moment, torque actually, to be equals to the rate of change of the angular momentum. So r cross p, right? And this and usually what we do is we also write r cross p, we define this usually to be L. So this is equals to d by dt of L, which is the same as L dot. And now you have the very similar equation, very similar to the linear momentum. There's also a conservation law of angular momentum. So if the external moment is equals to 0, if n is equals to 0, then this implies that L dot is equals to 0, and therefore the angular momentum is a constant. Right, that's all I had to say about the conservation laws. In the next video, we're going to have a look at the work done for a particle. So thanks for watching.